Okay, thank you very much to the organizers for the kind invitation to speak here at this workshop. So this is a mathematics talk. I'll be talking about counting surfaces on Calabi-Yau fourfolds. It's a joint work with Yonghan Bei from ETH Zurich, who's here this week, and Yeonjun Park from Seoul National University. And the first part of our project will appear on arXiv soon. So the plan today is to start with some motivation, namely, what do we do when we want to count curves? So this will be motivation from Gromov-Witten theory. And after this, I'll discuss 3 problems you encounter when you try to count surfaces on a fourfold. The first one is higher obstructions. The second one is a Hodge theoretic problem, namely a vanishing problem. And the third one, if there's time, I'll discuss how you should remove point and curve contributions when you count surfaces. And this has to do with wall crossing. Okay, so let me start with a little bit of background and motivation. So in Gromov-Witten theory, we fix an ambient space X. So since I'm an algebraic geometer, this is a smooth projective variety over the complex numbers. And here the goal is to count Riemann surfaces C inside of X, or in other words, smooth curves C inside of X. And we fix some of their topological data, namely the genus G and the degree beta, which is a class in the second homology. So if you want to do this effectively, you need to look at the moduli, the complete parameter space of such objects. In other words, you want to compactify the parameter space of objects you look at. And if you want to do this, you should allow degenerations of the map from C to X and of the curve itself. So the traditional way of doing this is using Kontsevich compactification. So this consists of maps from C to X, where C is now allowed to acquire nodal singularities. We furthermore fix the genus of the curve and the homology class beta. And to keep things under control, we require the automorphism group of the map to be finite. And then you have a nice compactification, Kontsevich compactification. In the special case where X is a Calabi-Yau threefold, this will have expected dimension 0. And you can simply count the number of points in the moduli space, and you weigh the count by the size of the automorphism group. So this makes you end up with a rational number, and that's your Gromov-Witten invariant. Well, if you want to get integers, you have to deal with multiple covers, and you have to actually consider Gopa-Kumar-Vafa invariance. But in reality, in general, on any X, this moduli space is horrible. It will be singular with many components. We don't know their dimensions. But in some sense, it doesn't matter because this horrible moduli space will have a class in homology which behaves as though the moduli space is smooth of the expected dimension. So this class in algebraic geometry was constructed by Bernd van Tecke and Lien Tian. And the degree, the real degree, is twice the virtual dimension, which in this setup is, well, the deformation space. So it's, well, the virtual dimension in general is the dimension of the space of deformations minus the dimension of the space of obstructions. And if you happen to look at a smooth curve, well, you look at the normal bundle N of your curve in your space, and the sections of that is the deformation space, and the H1 of the normal bundle will be your obstruction space. So this is the virtual dimension. And what makes this work is that this difference between the dimension of the deformation and obstruction space is purely fixed by the underlying topology of the problem. So in this case, if you do the calculation, you'll find that it's 1 minus the genus times the dimension of X minus 3, so I'm here discussing for general X, plus the integral over beta of the first Chern class of your ambient space. So in particular, if you're on a Calabi-Yau threefold, this first term vanishes. And if it's moreover, well, Calabi-Yau, then the second term vanishes and you get 0, as I already mentioned. And a crucial point, what makes this work, is that there are no higher obstruction spaces here. So these higher cohomology groups, they vanish. And this is quite important here. So today, the question we ask ourselves is, can we count surfaces, complex algebraic surfaces inside of, well, if we want any hope of doing this, we'll be taking here X to be a Calabi-Yau fourfold. So this is the leading question. Are there any questions? Okay, so the first obstruction that we encounter is the following. So henceforth, X will be a Calabi-Yau fourfold. And we now look at a complex surface S in X. Well, the very first issue is that we now have a second cohomology group, H2 of the normal bundle, which in general will not be 0. But there is some special structure when you're dealing with surfaces on a Calabi-Yau fourfold. Namely, this new cohomology group is actually dual to the deformation space, the sections of the normal bundle. So to see this, you actually observe that the canonical class of your surface is the second wedge of the normal bundle. And another piece of extra data is that we have a pairing on the obstruction space, H1 of the normal bundle. So the upshot will be that, yes, we are having a higher obstruction, but because we also have this pairing coming from Serre duality, we will actually be able to build a virtual class. Very roughly speaking, what you do is you go to your obstruction space and you fix a maximal real subspace on which the Serre duality pairing is real and positive definite. So then your obstruction space decomposes. And roughly speaking, you keep your deformation space and you replace the obstruction space by this real part. So this difference, in fact, is topological. So it's given by twice the holomorphic Euler characteristic of the surface minus the integral of gamma squared. So what is gamma here? So I'll always be denoting by gamma the fundamental class of the surface, and I'll also always identify it with its Poincare dual in cohomology. Okay, so I'll suppress that. So now I should be more precise about what the moduli spaces we'll be looking at. So what we want is we want a compact moduli space. So we want the surface to be allowed to degenerate. But we want to do it in such a way that we can keep this Serre duality pairing. So we want a compactification where we also have this pairing at the boundary. So then it's instead of stable maps or the analog, a convenient place to work then is the Hilbert scheme. So what we'll be doing is we fix our topological data now to be a surface class gamma, a curve class beta, and a number n. You can forget about this shift factor here. It's there for convenience. And we look at Grothendieck's Hilbert scheme of closed subschemes of X, where Z is allowed to have components of dimension 0, 1, and 2. And we fix the Chern character of the sheaf of functions on Z, and we fix it to be this V. So this is a nice compact space, and all the points in this space will have this Serre duality pairing on their obstruction space. And it turns out that in this setup, you can indeed define a virtual cycle of the moduli space. And this was first done by Borisov-Joyce in complete generality, and a more algebro geometric construction was subsequently given by Owen Thomas. The upshot here is that you get a virtual cycle, again in the homology of the moduli space, and the virtual dimension, the degree where this cycle lives, is given by this number. So remember, we fix gamma, beta, and n, so it's 2n minus the integral over x of gamma squared. But note, there's no 2 missing here. So previously we had a 2, here there's no 2. This is really the real degree. And another new feature of this theory is you can only construct this virtual class if there exists an orientation on the moduli space. So roughly speaking, what this means is at every point in the moduli space, we have the total derived global sections of the normal bundle. We can take its determinant, and Serre duality gave us a trivialization of this. And an orientation means a choice of square root of this, consistently done over the entire moduli space. So this is a difficult problem, and existence of orientations was shown by Tsao, Gross, and Joyce. So this is the background. I should also stress that the theory of Borisov, Joyce, and O. Thomas, it's not specific for surfaces. It works for moduli of sheaves on Calabi-Yau fourfolds in general. But it is very specific to Calabi-Yau fourfolds. So no other fourfolds or higher dimensions. So now the main thing I want to talk about is that this class is also not yet the right one if you're interested in counting surfaces. It is the right one if you want to consider points and curves on Calabi-Yau fourfolds. Are there any questions, comments? So now we get to the problem I'm really interested in, namely we take this O. Thomas virtual class, and let's go to the simplest example, the sextic Calabi-Yau fourfold. And well, the general sextic does not contain a plane, but let's say we're on a special sextic which contains a plane, and we calculate this number from the previous slide, and we find, unfortunately, that it's negative. In other words, this cycle of O and Thomas is trivial in this case. And there's in fact another way of seeing why you should expect zero invariance in this setup. Namely, if we look at a smooth family of sextics, and let's take the base contractible, then we can extend this surface homology class to all the fibers. So we extend gamma, which we fixed, to all of the fibers. And what's interesting then is you should think of this family as varying the complex structure on an underlying topological object. So yeah, we do have this class gamma in every fiber, but if you vary the point over the base, the Hodge type of this class gamma will vary. So it may not remain of type 2,2. And in fact, the definition of the Hodge locus is it's the locus in the base where gamma maintains Hodge type 2,2. So this is the locus of interest. So I'll always be denoting by X subscript B the fiber over a point B in the base. And then what happens is that the Hodge locus inside of this base also has codimension 19. And this tells you immediately that you should expect your invariance to be 0, because if you start with the Borisov, Joyce, O. Thomas virtual cycle on the Hodge locus, well, it's an invariant, so you should also be able to get the same answer. Well, you will get the same answer if you deform off the Hodge locus, but off the Hodge locus, the moduli space is empty, so the cycle is 0. And this is not a new phenomenon. If you study curves on a K3 surface, you have the same problem. Gromov-Witten theory of a K3 surface is trivial. So you only get non-zero answers if you take some trivial pieces out of the obstruction spaces of Gromov-Witten theory, and only then you get interesting answers. And this is, if you study the Katz-Klem-Vafa formula, this is a procedure you have to do. And in fact, our goal is to do a similar procedure here for Calabi-Yau fourfolds, for surfaces on Calabi-Yau fourfolds. And the answer will be neatly formulated in terms of an interesting bilinear form. So we fix X now an arbitrary Calabi-Yau fourfold, and we take some 2,2 class gamma on there. Then we have the following interesting bilinear form. So it's defined on H1 of the holomorphic tangent bundle. So this is the space of infinitesimal deformations of your Calabi-Yau, tensored by itself to C. And, well, a neat way of writing it is you take two shifted vector fields, V and W, and you contract your 2,2 class by these shifted vector fields, and you cup the result with a Calabi-Yau volume form. So then you get a 4,4 class, which you integrate to obtain a number. And because of these cohomological shifts, this is a symmetric bilinear form. And it has some interesting appearances both in physics and mathematics. So the mathematical interpretation is that if you have a smooth family of Calabi-Yau fourfolds over a smooth base, then the rank of this bilinear form is the codimension of the Hodge locus inside of the base. And to be precise, I'm assuming here that the Hodge locus is smooth and all the Kodaira-Spencer maps in the base are isomorphisms. And this bilinear form also seems to appear in physics, where it's the double derivative of the Gukov-Vafa-Witten superpotential. Okay, so then having this notation in place, what is the theorem? So the theorem is this. We fix a Calabi-Yau fourfold X and a Chern character where we have a surface class, a curve class, beta, gamma, gamma, beta, and n, a number. We fix an orientation on our Hilbert scheme of surfaces. Then there exists another virtual class, a reduced virtual class, again in the homology of the moduli space, and this time the degree in which it lives is the old number that you get out of the previous class, 2n minus integral over x of gamma squared, the surface class. But now, because of the reducing procedure that we carry out, we get an additional term. We make the obstructions smaller, the obstruction space, and that increases the dimension of the cycle by the rank of this bilinear form B gamma. And what's maybe immediately noticeable about this formula is that it's independent of your curve class beta. Okay, so this is the new term. And for instance, if you're having plane on a sec stick, these first two terms are minus 19. The second term is plus 19, so you get 0. So the second theorem is that this works in families. So if you have a family of Calabi-Yau fourfolds over a smooth connected base B, now let's assume that we fix a family of Chern characters over all the fibers. Right? So over each fiber B in the base, I fix a 2,2 class gamma, a 3,3 class beta, and a number n. So note, I already want my classes to lie in the Hodge locus here. So I'm fixing this in a family. To phrase this properly, you should fix a Hodge bundle, take sections of a Hodge bundle, but let me just do it pointwise. And let's assume that the rank of this bilinear form is constant. So in the base, you'll always, rank is lower semi-continuous, so you'll always have some open subset on which the rank is maximal, so let's just sit there. Then the statement is that if you take, okay, so first of all, unlike Gromov-Witten theory on the Calabi-Yau threefold, this in general is not a virtual dimension 0 theory, so you should put insertions. So let's say we have a nice family of insertions. Then the theorem is that this is an invariant, so this is constant over the base. So the way you remember this is a deformation invariant along the Hodge locus of your class gamma. So this is precisely the same as when you study curves on a K3 or general type surface. You use reduced Gromov-Witten theory. They're only deformation invariant along Noether-Lefschetz loci. Okay, are there any questions? So maybe one slightly mathematical slide. Well, maybe they all look mathematical. So what is roughly DID? So we start on this obstruction space, H1 of the normal bundle. And there's a very interesting map by Bloch. So when you have a surface on a variety, let's say here a surface on a Calabi-Yau fourfold, on the one hand you have obstructions to deforming the surface. On the other hand, you have obstructions to deforming the Hodge class. And there is a map called the semi-regularity map, which precisely relates those two obstructions. So it's a map from H1 of the normal bundle to the 1,3 forms of your fourfold. And once we're here, we do something specific to Calabi-Yaus. We take a shifted vector field. By the Calabi-Yau volume form, we can identify it with a 3,1 form. So if we have a 1,3 form and we cup it with a 3,1 form, we get a 4,4 form, which we integrate to a number. So what we get, so this linear functional on the obstruction space is what's called a cosection. So for each shifted vector field, we get a cosection on the obstruction space. And the goal is, roughly speaking, you want to take the intersection of the kernels of all these cosections as your new obstruction space. So you make the obstruction space smaller by looking at the kernels of all of these maps. In general, this procedure of using cosections was introduced by Kim and Lee, and in the fourfold setting, it was studied by Kim and Park. And this is what we technically use to obtain the previous two theorems. I should also stress that the two theorems that I just mentioned, they actually work in other settings. For instance, if you look at two-dimensional sheaves on a Calabi-Yau fourfold, or even higher rank sheaves, for all of those moduli spaces, we also have the virtual class, reduced virtual class, and deformation invariance along the Hodge locus. Let's do some examples. So let's call a surface semi-regular if this map of Bloch here, this first map SRS, is an injection. So the very first kind of sanity check is this example. A point in the moduli space, a surface is semi-regular, if and only if the moduli space is smooth of complex dimension half of this real virtual dimension at the point. So what this is saying is that if you're looking at the semi-regular locus of your moduli space, there this reduced virtual class is just a fundamental class. So it behaves well at those points. And in particular, if you, for instance, have a plane on a sextic, it's a semi-regular point, it's a rigid surface, and the reduced virtual dimension, as I already said, is 0. So it's an isolated point in your moduli space. An isolated, smooth point in your moduli space. The second example, so far I haven't actually told you what I mean by a Calabi-Yau fourfold. So I mean a smooth projective variety with trivial canonical bundle, but I allow abelian fourfolds and hyperkähler fourfolds. So in the second example, let's take a hyperkähler fourfold. So here we mean that the fourfold has a non-degenerate holomorphic two-form. And now let's suppose our surface is moreover Lagrangian, so meaning that the restriction of this holomorphic form to the surface is 0. So in this case, the virtual dimension is a very concrete number. It's the holomorphic Euler characteristic of the sheaf of 1 forms on your surface plus the rank of the restriction map. So if I have a 1-1 form on the fourfold, I can restrict it to a 1-1 form on the surface, and it's the rank of this map that appears here. So in particular, if you're interested in looking at Lagrangian planes on hyperkähler fourfolds, then this implies they will always be semi-regular, they're rigid, and the virtual dimension, the reduced virtual dimension of our class is 0 at these points. These are. The final example is maybe an illustration of Theorem 2. So let's maybe recall in Theorem 2, what we were doing is we had a family of Calabi-Yau fourfolds, curly X, over some connected base, curly B. Everything smooth here, smooth Calabi-Yau, smooth base. And we fixed a family of Chern characters, and we look at a family of Hilbert schemes with their reduced class. N, yeah, so N, yeah, roughly speaking, it's the number of points, but to be precise, it's the holomorphic Euler characteristic of O of your surface, so O of S. Yeah, holomorphic Euler characteristic, yeah. Yeah, to be precise, in the Hilbert scheme, yeah, it will be chi of O of Z, yeah, the holomorphic Euler characteristic. Yeah, I think this gamma should be close to what's called G4 at this conference, but maybe not quite. Maybe there's some shift. Yeah, and the reason we make this shift here is because then the virtual dimension has this particularly nice expression.
So this formula is something that we can kind of smell a little like tadpole.
Yeah, this in fact is one of the questions to the audience at the very end.
Okay.
No, but yeah, that is, yeah. This was what I was hoping to hear. Yes, okay, so now let's say we're in the setting of this family of Calabi-Yau fourfolds. Then over a smooth base. Then, yeah, the third example is the following observation. Namely, if you happen to have some point in your base where your invariant is non-zero, well, then this must mean that the moduli space is non-zero. So your 2-2 class must be represented by some surface. So it must be algebraic. Okay. But then the deformation invariance tells you this number is non-zero everywhere over the base. In particular, the moduli space is non-zero everywhere over the base. In particular, your 2-2 class gamma will be represented by an algebraic class everywhere over the base. You could make this observation too for Gromov-Witten theory, but since the Hodge conjecture is known for 1-1 classes, perhaps people didn't make a big deal out of it. But here, what you have is you indeed settle the variational Hodge conjecture if you find an invariant in your family which is non-zero for that specific class and that specific gamma. So recall the Hodge conjecture tells you that if you have any PP class with Q coefficients on any smooth projective variety, it should be Poincare dual to an algebraic cycle. And the first open case of it is for surfaces on fourfolds. So in principle, potentially it's useful for that. Are there any questions before we, so this is what I wanted to say about problem 2. So in the final part, I want to perhaps talk a little bit about problem 3, which is more about what kind of compactification of the moduli space you should work with. So what is problem 3? Well, the point is the Hilbert scheme, it contains all subschemes of dimension less than or equal to 2 with some fixed topological data. So schemes in here may have components that are 2-dimensional, but it may also have components that are 1 or 0-dimensional, which can float around freely. I mean, maybe if you already like the Hilbert scheme, this problem 3 is not a problem, but it could be that you may want to remove the curve and point contribution, or at the very least, you may not want these curves and points to move freely. So what we do is we introduce, so let's henceforth call the Hilbert scheme M-1. So we introduce 2 more moduli spaces, M0 and M1. So M0 will also parameterize surfaces, curves, and points, but we force the points to lie on the curve. And in M1, we also parameterize surfaces, curves, and points, but we force the points to lie on the curves, and the curves to lie on the surfaces, so there's some nestings. Let me make this mathematical in one slide. I mean, it's not so important, but the formal definition is as follows. As before, we fix a surface class gamma, a curve class beta, and the holomorphic Euler characteristic n. And we fix tau to be -1, 0, or 1. So remember, -1 is the Hilbert scheme case. I'll include it in this way. I'll rewrite the moduli space. And then by definition, m tau parameterizes pairs f, s. So f is a 2-dimensional coherent sheaf on your fourfold. S is a section of your sheaf. And we put 2 conditions. The 2-dimensional sheaf has no subsheaves of dimension less than or equal to tau. So this is an empty condition in case tau is -1. And the co-kernel of S must have dimension less than or equal to tau. So in the case tau is -1, it means this section is surjective, which means that F is actually the structure sheaf of some scheme. And what I didn't write is, of course, we fix this data. It has to have this fixed topological data above, where n is again the holomorphic Euler characteristic. So then the point is that these are compact moduli spaces. But what we can also do is the following. So if we have a pair in one of these 3 pair moduli spaces, we can also associate to it a 2-term complex in the bounded derived category of the Calabi-Yau fourfold. Namely, we view the section as a map from O to F. So this goes from pairs to two-term complexes. And then what we can show is that this is an embedding of these pair moduli spaces into moduli of Bridgeland stable complexes. I guess physicists may call this pi stable after Douglas. And to be precise, these are polynomial stable complexes. So this is quite familiar for curves on Calabi-Yau threefolds too, where Pandry-Pandey-Thomas did this too. They have the Hilbert scheme and the pair moduli space, and they again interpret them as parameterizing complexes in the derived category. But what's new in the fourfold setting is you have two pair moduli spaces, not just one. And I should also say that the tau is one case of this map was studied by Golampur, Yang, and Low. Okay, so in fact, yeah. Then the theorem that we have is that these three pair moduli spaces, M-1, M0, and M1, they are related by wall crossing. And they're actually related by the most classical interpretation of wall crossing. You have one space M with an action of the some special linear group. And then you have three linearizations, L-1, L0, and L1, determining your stability condition. And for each of these three, you take the GIT quotient, and you get these three moduli spaces. So they are related by classical wall crossing. And we can use this to find a rather general wall crossing formula conjecturally, between the tau is -1 space and the tau is 0 space. Remember, tau is -1 is the Hilbert scheme. And the wall crossing between tau is 0 and tau is 1 is more subtle, because there you're really forcing your curves on the surface, and this we only have in special cases. So for instance, if you have an elliptically fibered Calabi-Yau fourfold and all your classes are vertical over the base, then we have a precise wall crossing formula. So perhaps the final part of the talk I want to spend on discussing a local example, namely the simplest Calabi-Yau fourfold, C4, although it's non-compact. But maybe first I should ask, are there any questions up to this stage?
Could you explain, please, how this form of wall question is related to the usual one which we're used to? Did you think this is jumping across walls?
Yeah, so this you should, I will actually make it precise for C4, but this you should really view as the DTPT, Donaldson-Thomas, Pandry-Pandey-Thomas wall crossing. And we're not varying the polarization here, but I'll write down a precise formula for the C4 case. This may be, this may be something you want to see. Okay, C4. So we take coordinates. So I have until a quarter. I have 15 minutes, right? Or 10 minutes maybe. Yeah. Okay, that's more than enough. So I look at C4, and I use coordinates x1, x2, and x3. And I use the usual standard scaling action, but I do want to restrict to the Calabi-Yau torus, defined by T1, T2, T3, T4 is 1. So this preserves the holomorphic volume form of your Calabi-Yau. So now we want to count. Let's start on the Hilbert scheme side. We want to count two-dimensional torus-fixed subschemes, but we do want to fix some asymptotics at infinity. So the way we do this is send one of the coordinates xi to infinity, and then at infinity you have a curve which looks like this. So it's some infinite three-dimensional partition. And I didn't draw it, but you're also allowed to pile boxes in this center here. So if you worked with the topological vertex in 3 dimensions, you've seen these pictures. But this time we fixed this. So we fixed 4 of these at infinity. And we call them mu1, mu2, mu3, mu4. And we want to count surfaces where the curves at infinity are fixed. And, well, what you can already see from this picture, if you send a second coordinate to infinity, you actually get a finite partition. So if you send I and j to infinity, you get a finite partition. I call it lambda ij. Maybe it's redundant data, because if you know the mu i's, you also know the lambda ij's. But Okay, so then what we do is we define the topological vertex for C4. The way it's defined is you sum over all the two-dimensional subschemes where this asymptotics is fixed, and you weigh them by q to the power the number of embedded points. So we fix the asymptotics at infinity, but we are allowed to stick in as many points, embedded points, as we want. And then there are two features. So first of all, there's a term here, which is the term coming from T-localization. So if you do torus localization or T-Abbott localization, you get a 1 divided by the Euler class of the normal bundle. In fourfold theory, you're always supposed to take a square root. And also, since fourfold theory is not a virtual dimension 0 theory, you may want to put an insertion here. And I'll specify a nice choice of insertion on the next slide. So the localization formula in the fourfold setting was derived by O and Thomas. But a new feature of the theory is that every fixed point will come with a sign. So this is your choice of orientation. And these signs is really where the new feature of fourfold theory lies. So what is this insertion? A natural choice of insertion is an insertion we got from one of Nekrasov's papers. So I only wrote it down if Z is zero-dimensional. So what you do is you take the global sections of your scheme and you weigh them by a mass parameter. You take the total wedge and then you divide by the determinant and take a square root to symmetrize it. So this, in mathematics, we call this a K-theoretic insertion. And actually, for curves and surfaces, you should replace global sections by derived global sections. And then this term will become a rational function in the equivariant parameters, the torus parameters, T1, T2, T3, T4, and this mass parameter Y. And remember, we're always on the Calabi-Yau torus, so then the product of these TI's is 1. So the topological vertex for curves on C3 comes from physics, Aganagic, Clem, Marinho, Vafa. Actually, this is closer to the refined topological vertex in Iqbal, Koskas, Vafa. And in mathematics, there's Maulik, Nekrasov, Okunkov, Pandripande, and a whole bunch of other references. And I should say this topological vertex, if you study it for points, so we're enumerating surfaces, if you study it for points, it was first studied on C4 by Nekrasov, Piazzalunga, and in the curve case, in joint work with Yalong Cao and Sergei Monavari, who's from Utrecht. And the upshot is, this was the Hilbert scheme side, the tau is -1 side. You can also define a topological vertex for the tau is 0 side. There's a small caveat. On the tau is 0 side, the fixed points may not be isolated. So we only are able to define it when the T fixed loci are isolated. And for instance, this happens if you only study surfaces and points. So you don't allow embedded curves, but only surfaces and points. Then you're always having isolated T fixed point on the tau is 0 side as well. So it happens quite often, but not always. So then the conjecture is there is a choice of orientation, so a sign assigned to each fixed point, such that if you start with the Hilbert scheme generating function, and you divide by the point contribution, so all the asymptotics at infinity is empty, then you get the tau is 1 generating function. And this one is already better. For instance, if there are no embedded curves, then the right-hand side here is actually polynomial in Q. So yeah, you get rid of an infinite. So this looks very familiar, very similar to the traditional DT, PT, Donaldson, Thomas, Panripanda, Thomas wall crossing. And what's important here is, these signs are crucial. This only works if you assign precisely the right sign to every fixed point. So this choice of orientation is absolutely crucial. And the final thing I want to say, perhaps, is that this denominator here, so when you're counting just points on C4, so for this denominator there exists a closed formula. So this is, so when you're just counting points on C4, you have the following closed formula due to Nekrasov, Piazzalunga. I mean, this conjecture predates the other one. This was around 2017, if I'm remembering correctly. So here, Nekrasov, Piazzalunga, they consider supersymmetric Yang-Mills theory on C4, and they do supersymmetric localization, and then they get an explicit formula, the plathistic exponential of brackets T1, T2, T1, T3, T2, T3, the equivariant parameters, always satisfying T1, T2, T3, T4 is 1, divided by bracket T1, T2, T3, T4. And then there's this mass parameter, square root of y, square root of yq, square root of yq inverse. And in mathematics, recently with Jürgen Renemo, we proved this formula. And you can see this as an enumeration of four-dimensional piles of boxes, of solid partitions. So sort of this Donaldson-Thomas theory on fourfolds gives you a natural measure for how to enumerate solid partitions. It was first found in physics by Nekrasov Piazzalunga, but the geometry indeed gives their measure. So that's quite nice. And then let me end by a few questions. So indeed, as was already asked, is there a relation between this virtual dimension and the tadpole conjecture? Because at least they both have G4 squared and the codimension of the Hodge locus. Second question is, I mean, in Gromov-Witten theory, formulae most of the time come from physics, and then mathematicians try to prove it, and maybe some new cases. But in the case of surfaces, are there any predictions for or expectations for surface counting on Calabi-Yau fourfolds? And the final question is, it's not a virtual dimension zero theory, so there's a lot of choice you can make for the insertion. And one natural one we got from Nekrasov's work is this K-theoretic insertion, but perhaps physics will tell us what precise insertions we should look at. Similarly, in Donaldson theory or Fafa-Witten theory, physics often motivates what are natural insertions to look at. So here too you can ask, what are natural insertions? Okay, thank you very much.
So yes, can you please go back to that equation that you were suggesting is related to tadpole? Right, so here the rank of B gamma, if I understand correctly, is the number of massive directions. So you want that to be maximal rank for us.
Yeah, I guess ideally it seems from physics papers that you want this to be the H3,1, so all the complex moduli.
That's H31, and let's say you replace gamma with gamma by, well, I guess you can't replace by anything. Just the self-intersection of the holomorphic two cycles. So this in my talk was not the one, it was the mirror to the what the KGLT would have been doing. So it's not related to Euler characteristic, but the tadpole condition is related to. No, that's the Euler of the Riemann,
Right.
holomorphic part of the Euler of X, not of X, of the surface, not the fourfold, right? So there's no feature of the fourfold other than that.
Yeah, but it's not
Right, so
related.
here, yeah.
So it's G4, wedge G4, right? Which is gamma, wedge gamma.
But it seems indeed that in your work you always assume J wedge G4 is 0. So
So he's right.
Yeah.
Thomas is correct. This is gamma with gamma is G4 squared. So that's
Yeah.
pi, right? So that's pi over 24 for us. That minus sign. So that's pi over 24. So put it the other side. So you're saying that, and then you want the rank to be maximal. So H31 plus 2n. And n is the, so you're saying, so this is going to give you some bound on the holomorphic Euler characteristic of the surface. From that viewpoint.
yes, like suppose you want this, because of course there's no guarantee that this is non-negative, but yeah, if you want a non-trivial count, you would want this to be.
In the context that you want an ADS side, you want it to be non-negative.
Right, right. But what I don't know is, for instance, it's not true that you can cook up many examples where this number is not positive, so where it is actually negative, even after this reducing procedure.
No, those are examples similar to what we have in. I mean, there are things that we consider like tadpoles, and there are things that we consider conofiltry ones, like the rigid ones and so on. So those will have the bound of your negative. The ones which can be ample, like can move around and so on, will be positive. I'm assuming that we have had similar situation in your case. Rigid ones versus non.
Yes, that's right. So on the sextic, indeed, there are, if you increase the degree of your surfaces, this number can become positive. Yeah.
Right. That's the case out of interest of physics.
The positive ones.
Yeah.
Yeah. And is there, for physicists, is there like do you like negatively curved K3 or positively curved most? Like, should we be counting Fano surfaces, general type, or K3? General type. Uh-huh.
Because you want the things that are like bifolds, that have ample normal bundles and so on. You can move around, so they should be general type.
I see. So as four manifolds, they should be negatively curved. Yeah.
More questions?
Okay, I mean, what I did not get, maybe I'm just too naive, but why would we want all the surfaces to be negatively curved? I mean, you just said you want negatively curved surfaces.
Oh, you're asking me?
Yeah.
No, I was saying that if you want to have, suppose you wanted to be, so I'm reinterpreting what you're saying in the language of the software sketches, that is, if you take M5 brain wrapped around 4 holomorphic cycles, which is roughly the mirror of thing, not the usual, because you're going to the holomorphic side rather than special Lagrangian, then to get a small cosmological constant like theta, you won't have a big central charge. So you want these guys to be, so you want the moduli space of this surfaces to be big as possible. As big as possible means the normal geometry of this bundle is controlled by the fact that the dispersion mass is 0. So the more normal bundle condition means that these are the normal direction is relative canonical line bundle on the surface, which the condition that you want to be more of those means it's surface of general type.
Yeah, and at least you do indeed see this number growing if you would go to general type, because in here there's the H02 of your surface. So yeah, if you go very far into general type, that number grows, so and that comes with a plus sign here. So yeah, this virtual dimension would grow.
If you fix gamma with gamma to be the Euler characteristic of the Calabi-Yau over 24, let's say, how big can you make that n?
Uh-huh.
And if you want the rank to be H21, what's the biggest you can make n?
And this you really want H31, so big,
Yes,
big.
You want to have that's what we wanted. That's related to fixing all directions. Everything is mass level. The second derivative of that thing so potentially you want to be positive, not maximal, right?
Okay.
So you want rank to be maximal, and you want gamma with gamma to be pi over 24, and you want find what is the biggest you can have of these groups.
I see.
And related to my talk, that's not going to grow too much more than gamma with gamma.
I see. Hmm.
More questions?
Are there some bounds on M, like Castanova-like bounds?
Yeah, I don't think we really studied this, so not that I'm immediately aware of, but yeah, it may be that if you dive a little further, deeper into surfaces on fourfolds, that there are some. Yeah, in principle, I guess you can get it very high. So even on a sec stick, if you take 3 hyperplane sections, so something of type D1, D2, D3, and you make those DIs very large, then, but then of course the question becomes, yeah.
For three-folds, I think the bound is rather for negative, when n becomes negative.
Yeah, so, yeah, I think that shouldn't,
This seems to be related to what Kuhn was saying.
right.
We want negative n to cancel the rank on D.
Yeah, I think even on sec sticks, this can maybe not grow too much. But yeah, we haven't studied specific examples that much. Yeah.
Just to make a remark, the remarkable thing is kind of that it's kind of the first time I've seen it before, of course not, but that the number of stabilized moduli is kind of coming together, that the flux stabilizing them in some linear fashion, and that there is kind of an invariant on the locus